Hi everybody, we've been talking about complex fractions, so I thought I'd spring this one on you. This is the ultimate complex fraction, actually called a continuous fraction. 1 plus 1 over 1 plus 1 over 1 plus 1 forever. And you think, wow, that's a very interesting fraction. I wonder if it equals anything. Well, let's think about it this way. If I were to have 1 plus 1 over 1 plus 1, notice that that would equal 1 plus 1 half, which would, be 2 halves plus 1 half, which is 3 halves, right? Well, if I take this a step further, 1 plus 1 over 1 plus 1 over 1 plus 1, notice that this piece right here is exactly this part we just did right here. So this is going to be 1 plus 1 over 3 halves, which is 1 plus 2/3, right? Because you have to invert and multiply there. And 3/3 and 2/3 is equal to 5/3. Okay? So if I were to keep doing this, take another step. Again, notice this part right here, this 1 plus 1 over 1 plus 1 over 1 plus 1 is exactly this whole piece we just did in the previous step. So this is going to equal the 1 out front here plus 1 over the 5/3. And 1 over 5/3 is 3/5. And 1 plus 3/5 would be 5/5, and 3/5 is 8/5. Or just for good measure, let's do it one more time. Again, recognizing that all of this right here is this whole previous step here. Then it'd be 1 plus 1 over this answer that we just got was 8/5. And so that's going to equal 1 plus 5/8. And 8/8 and 5/8 is equal to 13/8. Okay? Well, you can probably begin to see that there's a nice pattern there that I don't have to, just keep doing this to recognize. If I start off with original 1, I didn't do that one, but 1 plus 1 over 1 plus 1 is 3 halves and 5/3 and 8/5 and 13/8. What you'll notice is that the numerator of the one before it becomes the denominator, and then I can get the numerator by just adding these two, the 8, right, 8/8 and 5/8 from the previous one. If you add these two numbers, you'll get the numerator. So 8 and 13 is 21/13, and then the next one's going to have a denominator of 21, and 13 and 21 is 34/21, and 55/34, and the next one have a denominator of 55, and add those as 89, and so on. Well, anyway, you can see I get this nice thing of numbers right here, and we can see what those numbers actually equal. They may be getting close to something. Let's try it out here. I got my calculator here. So obviously 1, that's just 1. 3 halves is 1.5. 5/3 is 1 2/3. That's 1.666 repeating. 8/5 is 1 3/5. That's 1.60. 13/8 is 1 5/8. That's 1.625, I believe. 21/13, that's about as far as my math skills go. Let's use our calculator. 21/13 is 1.615. Okay. How about the 34/21? 34/21 is 1.619. 55/34 is a 1.618 if you were to round to 3 decimals. And the 89/55 you can see that's also 1.618. Looks like it's bouncing around here around 1.618, doesn't it? Let's try the last one there just for good measure. 144 divide 89 is, again, if I round off, it'll be 1.618. So it seems like this is getting closer and closer to a number that's around 1.618. And in fact, that number is a very interesting number. It's so important it has a name. It's called phi, kind of like pi. You probably know about pi, 3.14159, and it never repeats and it never terminates. And this is the same sort of number. It's an irrational number, and it's approximately 1.618, and that's called the golden ratio or the divine proportion. Well, these numbers, this divine proportion, it shows up in many places in the real world, and one of the places, it was one of the first people to talk about it was a man by the name of Fibonacci, and Fibonacci was a Italian mathematician. He was actually the one who introduced the Hindu-Arabic numeral system to Western civilization. He lived around 1200 AD. And in this book that he wrote that introduced the Hindu-Arabic numeral system, it was called Fibonacci. And in this book, he posed this problem that said, if you introduce a pair of breeding rabbits into a field, and it takes 1 month for the rabbits to become mature, and then each month after that they will have a pair of baby bunnies, and it'll take a month for those baby bunnies to become mature, after which they will have a pair of baby bunnies. How many pairs of rabbits would there be at the end of a year? So here at the beginning, you've got one pair, and then at the end of the month they've just become mature, so you got one pair, and then at the end of the next month you've got the original pair and their pair of babies. That makes 2 pairs, and then this original pair, they can have another pair of baby bunnies, and so at the end of that month, while this pair is becoming mature, you have a total of 3. And you can see by just tracing this down that you get these numbers. At this time there would be 5, and 1, 2, 3, 4, 5, 6, 7, 8. And you see these numbers right here, those very numbers that we were talking about up here. And in fact, those are called the Fibonacci numbers. And you can obtain them by starting off with 1 and 1, and then just adding the 2 numbers before to get the next number in the sequence. So 1 and 1 is 2, and 1 and 2 is 3, and 2 and 3 is 5, and 8, and 13, and 21, and 13 and 21 is 34, 55, 89, and 144, and so on. And those are exactly the numbers, and so you can see that the successive ratios of the Fibonacci numbers are getting closer and closer to this interesting number phi that shows up in places like this. Well, here's another example. I keep bees, and it turns out that a male bee called a drone bee has a mother but no father. And the way that happens is if a queen bee lays an egg and she does not fertilize it, then it will develop into a male drone bee. But if she does fertilize it, then it will develop into a female worker bee. So if you have a male drone bee, its family tree would look like this. It would come from a female, a queen bee, and then that queen, being a female, had to have a mother and a father. All right, and then the mother, of course, came from a mother and father because that's a female, but the male came only from an unfertilized egg, so that male had only a mother and no father. And if you trace this down, you see that same pattern: 1 and 1 and 2 at this stage, 1, 2, 3, 1, 2, 3, 4, 5. And again, you're getting those Fibonacci numbers, the successive ratios of which are the golden mean, getting closer to the golden mean. All right, here's another example that shows up in nature. It turns out that the way things grow are related to this golden ratio that manifests itself in terms of these ratios of the Fibonacci numbers. Here's a pine cone, and you can see that if you look at the pine cone, which is of course where the seeds are stored, there's these little spirals. Okay, and it has to do with the way that the seeds grow. And if you count those spirals in one direction, as they're listed here in green, you can see that there's 8 of them. But you can also see how they spiral the other direction. If you look carefully, you can see the spirals in both directions. If you count them in that direction, there's 13. And of course, 8 and 13 are Fibonacci numbers. They're successive ones. And that is it's illustrating the manifestation of that golden ratio phi in the way that those seeds were packed in there and as the pine cone grew. All right. You can see that also in the way that flowers grow. You can see these spirals here. If you count them one direction, there's 21. If you count them the other direction, there's 34 in this little seed head of the flower. Okay. Turns out that the petals on flowers tend to be Fibonacci numbers. You can see this little yellow flower here has a total of 21 petals. You can see that same spiral shape inside of the seed head there. Here's the florals of a rose, right? If you count these, 1, 2, 3, 4, 5, 6, 7, 8 here, and then if you count the larger ones on the outside, there's 5, and of course 8 and 5 are the Fibonacci numbers. Here's another flower where there's a total of 8 petals, again a Fibonacci number. Here's a passion fruit flower. You can see these different arrays of flowers on it. Here there's 8 white ones, there's 55 blue ones, there's 5 of these little green ones, and 3 of these smaller ones up here, and all of those are Fibonacci numbers. Okay. The Fibonacci numbers can also be found in pineapples and bananas. There's the little spiral things on pineapples. Bananas have either 3 or 5 flat sides. I didn't know that until I found this on the internet. Pineapple scales have Fibonacci spirals in sets of 8, 13, and 21. The way that branches on various plants separate exhibit those same Fibonacci numbers, which is again an expression of the divine proportion or golden ratio. You can see here 1, and here there's 2, and 1, 2, 3, and 1, 2, 3, 4, 5, and so on. And then the number of flowers up here would be a total of 13, I believe it is, and that would make the examples of the Fibonacci numbers. Here's something else. This is called phyllotaxis. Turns out that when leaves grow on the branches of a tree, it's not just haphazard. In fact, they sort of spiral around so as to maximize the efficiency of the photosynthesis and the light that they're able to store for the plant. So if you take a leaf right smack on the, just right in the center of a branch, and you'll notice there's not one directly above it until some point further above it. And if you count around here, okay, you can see the thing, it spirals around. Here's 1 here, 2 leaves, 3 leaves, 4 leaves, 5 leaves, 6 leaves, 7. The 8th leaf, which is a Fibonacci number, is directly above it. And the number of times it spiraled around, 1, 2, 3, 4, 5, that is that's also a Fibonacci number. And the way that those leaves are arranged on the branch is called the phyllotaxis, I believe it's called. And the Fibonacci leaf arrangements of some common trees are these. The fraction represents the number of leaves per turn. So 1 to 2 would be an elm, a linden, lime, various grasses. 1 to 3, 2 to 5, 3 to 8, 5 to 13. Again, those are all Fibonacci numbers, and they different species have different manifestations of that golden ratio in the way that they grow. And when you look at the way humans grow, it's the same way. If you measure your height from the top of your head to your toes, and then you measure your height to your navel, you'll see that ratio is very close to 1.618. And you can do the same thing with your head, from your chin to your head to your top, and then from your eyes to your chin, and even from your arm right here, right, from your elbow down, and then from your hand, or from your whole shoulder down, and then from your elbow down. If you look at the way people's hands, you can put these in various ratios, 8 to 5 to 3 to 2, the various joints there, which are all Fibonacci numbers that are approximating the golden ratio. Okay, see it in the finger joints right here. All right, let's see, what else can we say? Oh, if you start with these Fibonacci numbers with squares, here's a square 1, here's another square, 1 and 1 is 2, and then I make a square on that. Okay, so this would be a 2 by 2 square, and then this would be a 3 by 3 square, and then this here, right, this is 3, 4, 5, so this would be a 5 by 5 square, and then if this is 5, this is like, this would be 3 more, right, so this is an 8 by 8 square. So this would be like 8, and this was, what do we say, this was 8 and 5, so this side's like 13, right? And an interesting mathematical relationship is this. Notice if you take 1 squared, that would be the area of this square, plus 1 squared, that's this one, plus this one, plus 2 squared. The area here would be 3 squared. This one here is 5 squared. And this one here is 8 squared. Well, you can see that all those squares add up to make this rectangle, and the area of that rectangle is 8 times 13, right? So it's sort of an interesting way. Those are all the Fibonacci numbers, and the squares of the Fibonacci numbers up to a certain point are just going to be that last Fibonacci number times the next one. Well, this rectangle, notice when you do all those squares together, you're getting a rectangle out of the whole picture there, and that rectangle is getting closer and closer to what's called a golden rectangle. The golden rectangle is said to be one of the most aesthetically pleasing shapes, and therefore you will find it in various places in art, and I'll show you some pictures of that here in a moment. Another thing you can do with this golden rectangle is if you connect the corners of each of these squares with a curve. It'd be nice if I could draw this a little better. I'm not the best artist in the world. But as you do that, you can see that you're getting a spiral. And in fact, that spiral ends up being exactly the cross-section of seashells, because as the sea creature grows, it sort of grows out of its shell. It excretes this substance that makes the shell. And as it grows, it just grows out of it, and that creates that spiral. Okay? So here you can see that. Right here, you can see the spiral that is representing that golden ratio that's manifested in the way it grows as well. You can also see that, very interestingly, here's a hurricane, and you can see that same spiral shape in the way that the hurricane is spinning around. Also, you can see that in the way that the rose petals grow as they spiral out as that's growing. You can even see it, that spiral shape in the various galaxies. They have these spiral galaxies, and they exhibit that same behavior that you can see there. Okay, so here's an example from art of that golden rectangle. This is a frontal picture of the Parthenon in ancient Greece. The ancient Greeks, they were aware of this. They understood what was beautiful, and so they proportioned their buildings and their other artwork according to this ratio, and this is how it manifested itself. Shows up very nicely there. Here's another example from art. Mona Lisa's face. This is the famous painting, one of the most famous in the world, recognized for its beauty. The face on the Mona Lisa is a perfect golden rectangle according to the ratio of the width of her forehead compared to the length from the top of her head to her chin. Here's another picture of the Mona Lisa where you can see the Fibonacci spiral on there that relates to the proportions of the painting. One more example comes from music. As we see these Fibonacci numbers that are a manifestation of the divine proportions show up all over in human experience. It seems to be the way things are created, the way they grow, the things we find beautiful. On the piano keyboard, there are 13 notes in an octave from one C to the next C. Of those 13, 8 of them are white and 5 of them are black. Before our current chromatic scale, there was a diatonic scale that had 8 notes, and before that there was a pentatonic scale that had 5 notes. Again, all of those are Fibonacci numbers. Stradivarius, who made the famous violins, he was aware of the golden ratio, and he was said to place the F holes in those violins in such a way that made them famous and accounted for some of their sound. Also for music, many of Mozart's sonatas divide into 2 parts exactly at the golden section point in almost all cases. People have conjectured if he did that consciously because his sister said he was always playing with numbers and was fascinated by math, or if he did it intuitively because he just understood what was beautiful and it just turned out to be that way. Likewise, Beethoven in his Fifth Symphony, that famous opening motto, appears not only in the first and last bars, but also exactly at the golden mean point of the way through the symphony. So I hope you guys find this interesting. There's a little video that follows this. I think you'll find it very interesting as well. See you next time.